All right, y'all go ahead and do the factoring and the math knowledge question. Pause the video, and then once everyone is finished, you can unpause the video, and I'll go over the correct answers. So on this factoring, you're going to do it as a factor by grouping. You're going to factor these two pieces separately. Those first two have an x to the 6th in common, and if you pull that out, you have 27x cubed plus 1. The second two have a negative 1 in common, and so if you pull that out, that'll give you the 27x cubed plus 1. Since these are the same, we can set it up as x to the 6th minus 1 times 27x cubed plus 1. Both of these can be factored further. This one can be factored as x cubed minus 1 times x cubed plus 1. And then I'm going to write the 27x cubed plus 1. And now each of those three can be factored as a sum or difference of cubes. So this x cubed minus 1 is going to factor like this, using your formula. The x cubed plus 1 is going to factor like this, again using the formula. And then I'm going to come to the second line and factor the 27x cubed plus 1. And so this would be your answer for your factoring. For the math knowledge question, it gives you the midpoint, and then it gives you one of the points, and it asks for the other one. Your midpoint formula, if this is your midpoint, you found it by adding your x's and dividing by 2, and adding your y's and dividing by 2. So our midpoint was 1, negative 6, and we have 9 plus a divided by 2. And then we have negative 13 plus b divided by 2. So 1 equals 9 plus a over 2. And negative 6 equals negative 13 plus b over 2. So you can multiply by 2. 2 equals 9 plus a. And negative 12 equals negative 13 plus b. So that means that your a is negative 7 and your b is 1. So the point is going to be negative 7, 1, which would be a. Okay, so moving on to lesson 77, we're looking at pumping fluids. So this is related to lesson 74, which was dealing with fluid force. This time we're going to be pumping the fluids out of our tank. So hopefully after this lesson you'll understand how to pump fluids out of a tank. So again, this one is related to lesson 74. And I'm going to tell you the formula, or I'm going to remind you of it. The weight density times the height times the area. And you would integrate it. So on this one, you are going to have to add in the length of the tank, because that's going to determine how much water you actually have to pump out, or how much oil or whatever your fluid is. So the formula for this one is now going to be, for the work, you're going to have the weight density times the height, and then instead of times the area, it's now times the volume, because it does depend on how long your tank is. In lesson 74, we didn't deal with the length of the tank, but now we have to. So we're going to integrate to be able to figure these out, and you're probably going to want to draw a picture. And we have a tank that is 6 meters tall, and it's 4 meters wide, and then it goes out 10. There's my tank. And it is completely full of water. So the whole thing is full of water. So that means that when we integrate, we're going to be going from 0 to 6, because our fluid is from 0 up to 6. The weight density of water, anyone remember? 9,800. For the height, you're going to set this up the same way you did in lesson 74. This here is 6. You have your y coming this direction, and then your h is coming this direction. And so h plus y equals 6. So your height is 6 minus y. So we're going to plug in 6 minus y. And then for the volume, well, the length here is always 4. It doesn't change. The depth is a 10. And then the height depends on your y value. So it's a dy. So now we're going to pull out 9,800 times 4 times 10. And you have 392,000. And then we're integrating 6 minus y, dy. So if you integrate that, you have 6y minus 1/2 y squared. And you're going from 6 to 0. So you plug in your 6. And then you plug in your 0, and you'll get a 0 on this one. And so we take 392,000 times 36 minus 18. So that's really just an 18 here. So you should end up with 7,056,000. And we're dealing with pumping something out. We're wanting to know how much work that is. So your units is going to be joules. So that's how you would set up that one. We'll look at another example. We have a triangular tank, and it tells us it's an isosceles triangle with side lengths of 5, 5, and 6, as shown, and it is filled with oil to a depth of 2 meters. We want to find the work done in pumping out of the top of the tank, assuming the weight density is 5,000 newtons per cubic meter. So we want to start by drawing our figure. On this one, I think it would be best to put the bottom of your figure at the origin. You don't have to do it that way, but I think that that'll help. Now we have our fluid. It's a depth of 2. So this number right here is going to be a 2. We know that this length is 5. And then the top side is 6. So this one is 3 and that one is 3. So we're going to integrate. And we're going to go from 0 to 2 because that's where our fluid is. Our weight density is 5,000. For our height, I'm hoping you figured out the pattern here. We're going up for our y, and then we come down for our h. And remember, I told you it goes to the top of the fluid or where the fluid gets pumped to. Now this one is pumping the fluid out of the top of the tank. So your height is coming from the top and going down. And so this whole part here is 4. So your y plus your h actually equals 4, not 2, because you're starting from where the fluid is getting pumped to. So it's getting pumped to a height of 4, and so that's why you put a 4 here instead of just a 2. Okay, so your height is going to be 4 minus y. And now we have to do our volume. Now on this one, the length here is changing. And it's changing by whatever the equation of this line is. So we're going to say y equals the slope. We go up 4 and over 3. And it goes to the origin, so that means that our y-intercept is 0. So if you solve that for x, you get 3 over 4y. So we're going to have 3 over 4y for our front side. Now it goes back 20, so that's our other part for the volume. And then the last part we need is the height. And so it's a change in the y value, so dy. Hopefully that makes sense for you. We're going to pull out the 5,000, the 3/4, and the 20. Oh, whoops, I forgot one part. This equation is only going to give us the area, the work in pumping out this half of our triangle, because we only dealt with the equation for the positive side. We did not look at this side here. So what we need to do is to put a 2 in front of our integral to make it so that it does both sides. Okay? Sorry, I forgot about that little 2 there. So now we pull out the 5,000, the 3/4, and the 20, and we're going to multiply it by the 2 that's already out there. And then you're going to have 4 times y minus y squared dy left to integrate. So we have y squared, and then that would be a 2, y cubed, and 1/3. We're going from 2 to 0. So 150,000 to 2 squared minus 1/3 2 cubed. And then when you plug in 0, you will get 0. So we get 150,000, and then 8 minus 8/3. So 8 minus 8/3 is going to be 16/3. And so if you multiply that by your 150,000, you end up getting 800,000. And again, your units is joules because you were dealing with fluid force. I mean, not just fluid force, you were dealing with pumping it out. You were dealing with a work. So again, we had to multiply it by 2 because this part here, where we found the equation of the line, was only for this right side of our figure. So you had to double it to get both sides. And it was an isosceles triangle, so you didn't have to worry about them being different. It got split in half, and so those 2 sides are the exact same. Looking at another example, we have a tank that is a semicircle. The diameter is 20, and it's filled to a depth of 4 meters. And then it says to set up an integral that could be evaluated to find the work required. So that means that we only have to set this one up. We don't actually have to evaluate it. So I'm going to start by setting it up by drawing my picture. We want to put our circle at the origin because that'll make for the easiest equation. Our fluid is a height of 4. The radius of this circle is 10. So that means that this number here is a -6 because it goes from -10 to -6. So when we set up our integral, we're going to go from -10 to -6 because that's where your fluid is. Your weight density is 6,000. On this one, we are wanting to pump the fluid to a point 20 meters above the top of the tank. So for your height, you're going to do 20 minus y. Because you're not just going h equals y, because we're getting 20 meters above the top of the tank. So 20 minus y. And then you're going to have your volume. So the length of your figure is going to depend on the circle equation, which we would say x squared plus y squared equals 10 squared, which is 100. So x squared equals 100 minus y squared. So x equals the square root of 100 minus y squared. So we can say square root of 100 minus y squared for our length. The depth of The tank, let's go back up here. Oh no, it's hold right here, is 40. And then your height is going to be the change in your y, so dy. And then this equation here only gave us for this side of the circle, so it only gave us this right side. So in order to get the left side too, we need to put a 2 out front. And so all of this would be your integral for this question. And then again, the book does give you the answer on page 298 if you want to figure out what that would integrate to be. But all it asked for was to set up an integral. So hopefully that helps you with this lesson of dealing with how to pump fluids out of a tank. Make sure that you do your homework tonight, 1 through 25, and then we can go over any questions you have tomorrow.